The very first experience one encounters when sitting before the control interface of a modern, high-power telescope is a profound realization of the density of the universe. When you look at the raw data returned by the charge-coupled devices, the digital sensors that have replaced the photographic plates of the past, you are presented with a field of view that, to the uninitiated, might appear to be largely empty space. However, the operational reality of astrophysics is quite different. The primary function of an initial observation is often technical. One must measure the focus of the instrument. To do this, astronomers analyze what is known as the point spread function. In an ideal optical system, a point source of light, such as a distant star, would appear as a singular point on the detector. In reality, due to diffraction through the telescope's aperture and atmospheric turbulence, if the telescope is ground-based, the light is spread out into a specific pattern. By analyzing this spread, one can calibrate the focus. But there is a secondary, more philosophical observation that occurs during this technical procedure. If you were to select a random sector of the celestial sphere, a patch of sky that appears completely devoid of light to the naked eye, and you were to interact with the digital interface, clicking into the darkness, increasing the magnification, and enhancing the contrast, you would discover that there is no such thing as empty sky. In every direction, at every level of zoom, there is structure. You will find a faint galaxy, barely a smudge of photons that have traveled for billions of years. You will find a dim star, a red dwarf perhaps, lurking in the local galactic neighborhood. The sky is absolutely, completely saturated with astronomical objects. It is a solid wall of matter and energy. This density presents a magnificent reality, but it simultaneously introduces a significant observational challenge. When searching for a specific moving object within our own solar system, the background is not a blank canvas. It is a crowded tapestry of static noise. To find a new planet, one must take this dense field of stars and galaxies and ask a singular, mathematically precise question of every single point of light. Did you move relative to the background since the last observation? We are here to discuss the architecture of our solar system, a structure that we often assume is fully mapped and understood. Yet, the history of astronomy is a history of expanding boundaries. We must begin by establishing the context of planetary discovery, as it informs the current search for a massive, hypothetical object known as Planet 9. For the vast majority of human history, the inventory of the solar system was static. The ancients identified the wandering stars, or planetae in Greek. These were the objects that moved against the fixed background of the constellations. There were 6 known bodies: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. These worlds are sufficiently bright to be visible to the unaided human eye. Their motions were tracked by the Babylonians, the Greeks, the Maya, and the Chinese. They defined the cosmology of civilizations for millennia. Saturn represented the absolute boundary, the final frontier of the system, beyond which lay only the sphere of fixed stars. This paradigm remained unchallenged until the late 18th century. The expansion of the solar system required the development of optical aid. In 1781, Sir William Herschel, a musician and amateur astronomer living in Bath, England, was conducting a systematic survey of the night sky. He was not looking for a planet. He was searching for binary stars, pairs of stars that orbit one another, to measure stellar parallax. Using a telescope of his own construction, a reflector with a speculum metal mirror, he noticed an object in the constellation Gemini that did not behave like a star. It had a perceptible disk, whereas stars remain point sources even under high magnification. Herschel initially identified the object as a comet. This was the safe, conservative assumption. Comets were known transient visitors. Planets were permanent and divine. However, subsequent observations of its orbit revealed that it lacked the characteristic tail of a comet, and more importantly, its motion was too slow and too circular to be a typical comet. It moved in a nearly circular path well beyond the orbit of Saturn. Herschel had discovered Uranus, doubling the known radius of the solar system in a single night. This was the first time in recorded history that humanity had added a planet to its inventory. The discovery of Uranus is critical because it set a precedent for the relationship between observation and mathematics. Once Uranus was identified, astronomers began tracking its position with immense precision. They retroactively found it on older star charts, where it had been mistaken for a star. By the mid-19th century, a problem had emerged. The orbit of Uranus was not following the path predicted by Isaac Newton's law of universal gravitation. It was drifting. It was accelerating and decelerating in a manner that could not be explained by the gravitational influence of the known planets, Jupiter and Saturn. There were two possibilities. The first was that Newton's laws were fundamentally flawed at great distances. The second, more intriguing possibility was that there was another, unseen mass further out, a perturbing body that was gravitationally tugging on Uranus. This led to the discovery of Neptune, a triumph not of the telescope, but of the pen. In 1846, the French mathematician Urbain Le Verrier, and independently, the British mathematician John Couch Adams, calculated the precise location of this hypothetical body based solely on the irregularities in Uranus's motion. Le Verrier sent his calculations to the Berlin Observatory. On the very night the letter arrived, the astronomer Johann Galle pointed his telescope at the predicted coordinates. Less than 1 degree from Le Verrier's calculated position, he found Neptune. This was a seminal moment in physics. It proved that gravity could be used as a probe, that invisible objects could be seen through their influence on visible ones. This is the exact methodological foundation we rely upon today in the search for Planet 9. We must address the status of Pluto to understand the modern definition of the outer solar system. For decades following its discovery in 1930 by Clyde Tombaugh, Pluto was considered the 9th planet. However, its discovery was arguably serendipitous. It was found during a search for a massive planet X that was thought to be perturbing Neptune, but we now know those perturbations were observational errors. Pluto turned out to be tiny, smaller than Earth's moon. Its classification as a major planet became untenable in the early 21st century, not because astronomers wanted to demote it, but because our understanding of the neighborhood changed. We discovered the Kuiper belt, a vast circumstellar disk of debris beyond the orbit of Neptune. Pluto was not a lonely outpost. It was merely one of thousands of icy bodies. When objects of similar size, such as Eris, were discovered, the International Astronomical Union was forced to redefine what constitutes a planet. The criteria are threefold. A body must orbit the Sun, it must be spherical under its own gravity, and crucially, it must have cleared its orbit of other debris. Pluto fails this third criterion. It is a member of the Kuiper belt swarm, influenced by the gravity of Neptune, rather than a dominant gravitational master of its own domain. This brings us to the current era and the hypothesis of Planet 9. The argument for its existence is not based on direct observation, but on the same logic that predicted Neptune: gravitational anomalies. In the vast, frozen expanse of the Kuiper belt, beyond the orbit of Neptune, there is a population of small, icy bodies known as trans-Neptunian objects. Most of these objects orbit in a relatively predictable disk. However, as we observe the most distant of these objects, those with extremely elongated orbits that take them hundreds of astronomical units away from the Sun, we notice a striking pattern. If the outer solar system were governed solely by the known planets, the orbits of these distant objects should be oriented randomly. Their points of closest approach to the Sun, known as perihelia, should be scattered evenly around the solar system, 360 degrees in all directions. Furthermore, the tilt of their orbits relative to the plane of the solar system should be random. This is not what we see when we analyze the orbits of the most distant, stable Kuiper belt objects, specifically those that are detached from the direct gravitational scattering of Neptune. We find that they are clustered. They are all swinging out in the same physical direction in space. Their orbits are physically aligned. Imagine a series of distinct elongated ellipses, all pointing toward the same quadrant of the sky. Mathematically, the probability of this clustering happening by pure chance is exceedingly low. It is akin to taking a handful of pencils, throwing them in the air, and having them all land pointing exactly north. The statistical significance is overwhelming. There must be a physical mechanism forcing these orbits into this alignment. The most robust explanation for this alignment is the existence of a massive, unseen perturber, a ninth planet. To maintain this specific clustering of Kuiper belt objects, this planet must have specific physical characteristics. Theoretical models and computer simulations run by astrophysicists like Konstantin Batygin and Mike Brown at Caltech suggest that Planet 9 has a mass approximately 5 to 10 times that of Earth. This places it in a category of planetary mass that is common in the galaxy but absent in our own solar system, a super-Earth or sub-Neptune. It is likely a gaseous or icy world, smaller than Uranus and Neptune but significantly more massive than the terrestrial planets. The orbit of this hypothetical body is immense. It is highly elliptical, meaning it is not a perfect circle but a stretched oval. Its average distance from the Sun is likely hundreds of times the distance between the Earth and the Sun. To put this in temporal perspective, while Earth completes one revolution around the star in 1 year, and Neptune takes 165 years, Planet 9 would take between 10,000 and 20,000 years to complete a single orbit. The last time this planet was at its current location in its orbit, human civilization was in the Paleolithic era. We were hunter-gatherers painting in caves. The sheer scale of this orbit is difficult to grasp. It effectively creates a shell around the solar system, bounding the region of the Sun's dominant influence. One might ask, if we know its mass and its orbit, why have we not seen it? The answer lies in the physics of light and the vastness of the search area. We detect planets primarily by the sunlight they reflect. The intensity of this reflected light is governed by the inverse square law. Applied twice, the sunlight must travel from the Sun to the planet, diminishing in intensity as the square of the distance. Then, that feeble reflected light must travel from the planet back to Earth, again diminishing as the square of the distance. The total brightness of the object therefore drops as the distance to the fourth power. An object that is twice as far away is not twice as dim. It is 16 times dimmer. Planet 9 is so distant that it would be incredibly faint, likely hovering at the very limits of detection for our current survey telescopes. Furthermore, because its orbit is so large, the search box, the area of the sky where it could be located, is enormous. We are not looking for a needle in a haystack. We are looking for a slightly moving speck of dust in a field of static dust, without knowing exactly which field to look in. We know the path it travels, but we do not know where it is along that path. It is likely near its aphelion, the point in its orbit farthest from the Sun, simply because a planet spends the majority of its time in the distant, slow-moving part of its elliptical orbit. Kepler's second law of planetary motion dictates that a planet sweeps out equal areas in equal times, meaning it moves much faster when close to the star and much slower when far away. Therefore, statistically, it is most likely to be at its dimmest and slowest right now. There is a fascinating, albeit speculative, alternative hypothesis regarding the nature of this gravitational perturber. While the mathematics of the orbital clustering strongly suggests a mass of 5 to 10 Earths, the equations of gravity are agnostic regarding the composition of that mass. Newton's laws do not care if the mass is made of rock, ice, gas, or exotic matter. They only care about the mass itself. Therefore, it is theoretically possible that the object is not a planet at all, but a primordial black hole. Unlike stellar mass black holes, which form from the collapse of massive stars and are many times the mass of the Sun, primordial black holes are hypothetical objects that may have formed in the high-density environment of the very early universe, mere fractions of a second after the Big Bang. If Planet 9 were actually a primordial black hole with a mass of 5 Earths, its physical size would be vanishingly small. It would have an event horizon, the radius of no return, roughly the size of a grapefruit or a bowling ball. Such an object would be completely invisible in the optical spectrum. It would reflect no sunlight. We would only be able to detect it through its gravitational lensing effects on background stars, or perhaps through the annihilation of dark matter particles in its vicinity, producing gamma rays. While this hypothesis is consistent with the gravitational data, it is generally considered less likely than the planetary hypothesis simply because we know planets exist and form commonly, whereas we have yet to confirm the existence of primordial black holes. However, until the object is directly observed, the possibility remains a valid solution to the mathematical problem. Let us return to the nature of the planet itself and the context of our solar system's formation. One of the enduring mysteries of our system is the stark division between the inner rocky planets and the outer gas giants. We have Mercury, Venus, Earth, and Mars, small, dense, silicate bodies with iron cores. Then beyond the asteroid belt, we have Jupiter and Saturn, massive giants composed primarily of hydrogen and helium, and Uranus and Neptune, the ice giants composed of heavier volatile elements like water, ammonia, and methane. Planet 9, if it exists, likely fits into the ice giant category. The standard model of planetary formation, known as core accretion, suggests that planets form from the protoplanetary disk of gas and dust that surrounds a young star. Dust grains coagulate into pebbles, pebbles into boulders, and boulders into planetesimals. In the outer regions of the system, beyond the frost line, temperatures are low enough for volatile compounds like water to freeze into solid ice. This increases the amount of solid material available for building planets, allowing the cores of the outer planets to grow large enough, roughly 10 Earth masses, to begin rapidly accreting gas from the nebula. This explains why Jupiter and Saturn are so massive. However, the dynamics of the early solar system were likely chaotic. We believe that the giant planets did not form in their current orbits. They likely migrated. The grand tack hypothesis and the nice model suggest that Jupiter and Saturn moved inward and then outward, while Uranus and Neptune were scattered further out into the disk. It is entirely plausible that during this era of gravitational billiards, an additional planetary core, a fifth giant, was ejected from the inner region. Instead of being completely expelled from the system into interstellar space to become a rogue planet, this object could have interacted with the gas of the solar nebula or other bodies, slowing it down just enough to settle into a distant, stable, highly elliptical orbit. This ejected core would be our Planet 9. This brings us to a fundamental concept in orbital mechanics, the nature of stability and chaos. We often think of the solar system as a clockwork mechanism, a perfect machine that ticks with absolute predictability. In reality, the solar system is a chaotic system. This does not mean it is random, but rather that it is highly sensitive to initial conditions. This concept, known mathematically as the Lyapunov time, defines the horizon of predictability. For the solar system, this horizon is tens of millions of years. Beyond that timescale, we cannot precisely calculate the positions of the planets because minute gravitational interactions, the tiny tug of one planet on another, compound over time. When we say a planet orbits the Sun, we are simplifying the physics. In the framework of general relativity, the planet is following the curvature of spacetime created by the Sun's mass. It is, in a very real sense, falling. A planet is an object that is perpetually falling toward the star but has enough tangential velocity, sideways speed, to miss it. Planet 9 is falling around the Sun on a trajectory that takes it incredibly far, barely tethered by the Sun's gravity at its furthest point. It is walking the edge of the abyss, bound to the system by the feeblest of gravitational threads. The presence of Planet 9 also serves to explain other anomalies in the solar system. For instance, the Sun's rotation axis is tilted by about 6 degrees relative to the plane of the planets. If the solar system formed from a single spinning disk, the Sun's equator should be perfectly aligned with the orbital plane of the planets. This 6-degree tilt has been a long-standing puzzle. The gravitational torque exerted by a massive, distant Planet 9 over the 4.5 billion-year history of the solar system provides a mathematical mechanism to explain this tilt. It slowly pulls on the orbits of the other planets, causing the entire plane of the solar system to wobble slightly, creating the appearance of a tilted sun. Now, let us discuss the methodologies of the search. How does one find a moving object that is potentially 500 or 600 astronomical units away? The challenge is not just the faintness, but the data processing. Traditional astronomy involved a human eye at an eyepiece. Modern astronomy involves vast datasets and algorithms. To find Planet 9, astronomers use a technique called shift-hand stack. Because the planet is so dim, a single exposure from a telescope might not capture enough photons to distinguish it from the background noise. However, if you take multiple images over time and shift them according to the predicted motion of the planet, you can stack them on top of each other. The light from the static stars will smear out, but the light from the planet will pile up in the same pixels, increasing the signal-to-noise ratio. This requires knowing how the planet moves, which brings us back to the orbital models. We are scanning specific tracks across the sky where the gravity of the planet is most likely to be located based on the clustering of the Kuiper belt objects. We are essentially triangulating its position. The search is currently being conducted using some of the premier instruments on Earth, such as the Subaru telescope in Hawaii. But the game changer will be the upcoming Vera C. Rubin Observatory. This facility will conduct the legacy survey of space and time. It will image the entire visible sky every few nights with a massive wide-field camera. It will create a motion picture of the universe. If Planet 9 is there, and if it is not in the deepest recesses of the galactic plane, where the background star density is too high, the Rubin Observatory should find it. The role of artificial intelligence in this search cannot be overstated. We have reached a point where the volume of data exceeds human capacity for analysis. There are simply too many sources of light to check manually. Machine learning algorithms, specifically convolutional neural networks, are being trained to recognize the specific signature of a moving solar system object against the background of stars and galaxies. These AI systems can filter out false positives, cosmic rays hitting the detector, satellite streaks, and variable stars, leaving astronomers with a manageable list of candidates to verify. The astronomer of the 21st century is less of an observer and more of a data scientist. The romantic image of the lone scientist shivering in a telescope dome has been replaced by the scientist analyzing code and databases in a server room. We must also consider the philosophical implications of this search. The possibility of a 10th planet, or rather, a reinstatement of the number 9, speaks to our fundamental need to understand our environment. We live on a small rock orbiting a typical star, but our local environment, our solar system, is our cosmic backyard. To not know what is in our own backyard is a profound gap in our knowledge. If Planet 9 exists, it is likely the dominant gravitational body of the outer solar system. It would control the dynamical evolution of the Kuiper belt and the Oort cloud. It would be a sibling to Neptune and Uranus, holding secrets about the formation conditions of our system that have been frozen in time for billions of years. The skepticism surrounding the existence of Planet 9 is healthy and necessary in science. Extraordinary claims require extraordinary evidence, as Carl Sagan famously postulated. The evidence we have now is indirect. It is gravitational forensics. We see the footprints, but we have not seen the walker. Critics argue that the clustering of Kuiper belt objects could be an observational bias. Perhaps we are only finding objects in that direction because that is where we have looked the most, or because weather conditions and the galactic plane make other directions harder to survey. While rigorous statistical analysis suggests the bias is not strong enough to explain the signal, the possibility remains until the planet is imaged. Let us dig deeper into the concept of observational bias. This is a critical concept in statistical astronomy. Imagine you are looking for keys lost in a dark field, but you only look under the streetlights because that is where the light is. You might find objects there, but it doesn't mean objects don't exist in the dark. In the context of the Kuiper belt, we detect these distant rocks when they are closest to the sun, at perihelion, because that is when they are brightest. If their perihelia are clustered in a specific part of the sky, is it because they are actually clustered, or because we have only pointed our telescopes in that direction? The team advocating for Planet 9 has spent years quantifying this bias. They have accounted for where telescopes have pointed, the sensitivity of those surveys, and the weather conditions during those surveys. Even after subtracting these biases, the clustering signal remains statistically significant. The alignment of the orbits cannot be easily explained away as a trick of the data. Furthermore, there is the specific nature of the orbits. We are not just talking about their orientation in 2D space. We are talking about the argument of perihelion, a specific orbital element that defines the angle between the point where the object crosses the plane of the solar system and the point where it is closest to the Sun. The known distant KBOs have arguments of perihelion that are also clustered. Dynamical simulations show that Planet 9 naturally produces this specific confinement. It acts as a shepherd. Its gravity prevents the orbits of these KBOs from precessing, rotating over time, in a way that would destroy the alignment. Without Planet 9, the orbits should have randomized billions of years ago. The fact that they are still aligned implies an active, ongoing maintainer of order. Let us speculate on the physical appearance of Planet 9 should we ever resolve it into a disk. Given its mass and distance, it is almost certainly a cold, dark world. Its atmosphere would be dominated by hydrogen and helium, the primordial gases of the nebula. However, at such low temperatures, close to absolute zero, gases like methane would condense out. Methane absorbs red light and reflects blue, which gives Uranus and Neptune their characteristic hues. Planet 9 would likely be a deep, dark blue, perhaps even darker than Neptune. It would receive so little sunlight that from its surface, or rather from the cloud tops, as it likely has no solid surface, the Sun would appear merely as the brightest star in the sky, not a resolved disk. Day and night would be almost indistinguishable concepts. It is a frozen, lonely sentinel on the edge of interstellar space. The potential discovery of Planet 9 would also provide a laboratory for understanding super-Earths. Exoplanet surveys, such as those conducted by the Kepler Space Telescope, have shown that the most common type of planet in the Milky Way galaxy is a planet with a mass between that of Earth and Neptune. Yet, our solar system lacks a representative of this most common class. We have a gap between Earth would fill this gap. It would provide us with a local example of the galaxy's most typical planetary outcome. Understanding its internal structure, its magnetic field, and its atmospheric dynamics would revolutionize our understanding of planetary physics on a galactic scale. Returning to the historical parallel, the current state of the search for Planet 9 feels remarkably similar to the years preceding the discovery of Neptune. In the 1840s, there was a mathematical prediction, a sense of confidence among the theorists, and a difficult observational challenge. The difference today is the technology. We are not relying on the human eye scanning star charts. We are relying on petabytes of digital data and silicon intelligence. But the fundamental human drive remains the same, the desire to map the unknown. There is also a human element to this scientific endeavor. The collaboration between theorists and observers is essential. In the transcript provided, the interaction between the astrophysicist and the host highlights the accessibility of this science. We are discussing concepts that are mathematically rigorous, Hamiltonian dynamics, secular perturbation theory, but the core idea is simple. Gravity tells the truth. Matter influences matter. If you see something moving strangely, something else is pushing it. This principle holds from the falling apple of Newton to the distant, frozen orbits of the Kuiper belt. The notion of the solar system having an edge is also being challenged. Where does the solar system end? Is it at the orbit of Neptune? Is it at the heliosphere, where the solar wind meets the interstellar medium? Or is it defined by gravity? If Planet 9 exists at 500 O, it extends the gravitational reach of the planetary system significantly. But beyond that lies the Oort cloud, a theoretical sphere of billions of comets that extends perhaps halfway to the nearest star, Proxima Centauri. Planet 9 would be the bridge between the classical solar system and this distant Oort cloud. It might even be responsible for perturbing Oort cloud comets and sending them plunging toward the inner solar system, creating the long-period comets we observe in our skies. Let's consider the concept of orbital resonance, which is central to the Planet 9 hypothesis. Resonance occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other, usually because their orbital periods are related by a ratio of small integers. For example, Pluto and Neptune are in a 2:3 resonance. For every 3 orbits Neptune completes, Pluto completes 2. This resonance prevents them from colliding. Planet 9 is hypothesized to be in resonance with the distant Kuiper belt objects it shepherds. It protects them. By confining them to specific orbits, it ensures they do not cross its path and get ejected. This gravitational shepherding is a mechanism we see throughout the solar system, most notably in the rings of Saturn, where small moons maintain the structure of the ring gaps. The same physics that sculpts the delicate rings of Saturn is likely sculpting the architecture of the entire outer solar system on a massive scale. We should also touch upon the David Bowie reference mentioned in the source material. It reflects the cultural integration of astronomy. When objects are discovered, they need names. The International Astronomical Union has strict naming conventions, usually mythological deities associated with creation or the underworld for TNOs. But the informal naming, the playful association of a mysterious, distant starman or planet with cultural icons, reveals the human affection for the cosmos. It reminds us that astronomy is a human activity, driven by curiosity and imagination as much as by calculus. The search for Planet 9 is also a race against time and light pollution. As we launch more satellite constellations, tens of thousands of communication satellites, the low Earth orbit environment is becoming crowded. These satellites leave bright streaks in telescope images, complicating the search for faint objects. The filling up of the sky mentioned at the beginning of our discussion is happening literally, with artificial objects. The pristine darkness required to spot a magnitude 24 object is becoming a rare resource. This adds urgency to the work of the Rubin Observatory and other ground-based surveys. Let us delve into the physics of the invisible. When we discuss seeing a black hole or a dark planet, we are really discussing the interaction of light and gravity. If Planet 9 is a black hole, the grapefruit analogy is helpful for size but misleading for impact. A 5 Earth mass black hole would have an accretion disk if it were passing through a dense region of dust, which would emit X-rays. However, out in the Kuiper belt, the vacuum is high. There is very little gas to accrete. Therefore, it would remain radio-silent. This makes the gravitational method the only method of detection. It forces us to rely entirely on the indirect evidence of orbital mechanics. It is the ultimate test of our trust in Newton and Einstein. The trajectory of the Kuiper belt objects, specifically an object named Sedna, is worth a detailed look. Discovered in 2003, Sedna was the first major anomaly. Its closest approach to the Sun is 76O, far beyond the influence of Neptune. It never gets close enough to Neptune to be scattered by it. So how did it get there? Who gave it the energy to reach that orbit, and who took away the energy to prevent it from returning closer to the Sun? Sedna is a detached object. It exists in a no-man's land. Planet 9 provides the answer. It lifted Sedna from a more conventional orbit and parked it in this isolated region. Since the discovery of Sedna, we have found more such objects, 2012 VP-113 and others, all sharing these detached, aligned characteristics. Each new discovery adds a data point to the Planet 9 regression analysis, tightening the constraints on its orbit and mass. The concept of falling mentioned earlier deserves re-emphasis. In orbit, you are in a state of perpetual freefall. The International Space Station is falling toward Earth, but it is moving sideways so fast that the Earth curves away beneath it. The planets are falling toward the Sun. This dynamic equilibrium is what holds the system together. But in the outer reaches, where the Sun's gravity is weak, the orbital speeds are incredibly slow, perhaps a few hundred meters per second, compared to Earth's 30 kilometers per second. At these low speeds, the delicate nudges from a distant massive planet can have profound cumulative effects over billions of years. It is a slow-motion dance of gravity, played out over timescales that dwarf the history of our species. To conclude this extensive overview, we must recognize that the solar system is not a finished painting. It is a work in progress. It is dynamic, evolving, and still hiding secrets in its shadows. The hypothesis of Planet 9 is the most compelling current theory to explain the observed architecture of the outer system. Whether it turns out to be a massive ice giant, a primordial black hole, or a manifestation of physics we do not yet fully understand, the pursuit of this object pushes the boundaries of our technology and our intellect. We are scanning the darkness, pixel by pixel, stacking images, training artificial intelligence, and analyzing the faintest whispers of gravity. We do this because, as the source text implies, the sky is jammed with astronomy. It is full of questions, and the question of what else is out there in our own home system is one of the most primal and exciting questions we can ask. The ninth planet, if it is there, is waiting. It orbits in the deep freeze, a ghost in the machine of the solar system, its presence felt but its face unseen. The mathematical arrow points to its existence. Now, the telescopes must catch up. Until then, it remains the great phantom of modern astrophysics, a reminder that even in the 21st century, the era of planetary discovery is not necessarily over. We may yet have one more world to add to our maps, one more wandering star to track across the velvet backdrop of the eternal night. This is the beauty of science. The map is never truly complete. There is always something more on the edge of the visible.